As the demand for mission-aligned AI capabilities grows, many integrators and solution teams are navigating the challenge of pairing performance with compliance. Like all emerging technology within the U.S. government, we've seen that success often hinges on choosing a compute strategy that supports the realities of the ATO process without slowing down innovation. With the growing need and focus on AI systems within the industry, I have put together the top 4 considerations for choosing the correct AI infrastructure. On the screen, you see point number 1, unified compute platform reduces friction. AI and large data compute can be a complex architecture. When adopting a full stack compute platform from CPUs to accelerators to orchestration, the integration process becomes dramatically smoother. The difference is becoming more apparent as organizations build AI supporting infrastructure. Folks, it's not the server, network, storage environment that we built 10 years ago. In today's, especially federal landscape, deploying secure, scalable AI isn't just about finding the best GPU or CPU. It's about creating an architecture that's cohesive, supportable, and efficient from top to bottom. One best practice is the move towards a unified AI compute platform that combines high-performance CPUs, GPUs, and a transparent software stack, all from a single ecosystem. An end-to-end integration reduces the need to stitch together solutions from multiple vendors. This is important, especially when we're navigating the complexities of the ATO process under frameworks like RMF. Having a consistent hardware and software environment simplifies documentation, compatibility testing, and risk assessment, key pain points that often delay authorizations. Additionally, adding capacity in a single ecosystem is often a non-disruptive change to the ATO process, which basically means that you don't have to redo the ATO. If you are an integrator in a fluid U.S. federal demand environment, this capability to have non-disruptive change to the environment is huge. Unified platforms also provide technical advantages. When CPUs and GPUs are designed to work together, sharing optimized memory pathways and interconnects, it minimizes performance bottlenecks during AI training. It can even unlock novel architectures like unified memory pools or disaggregated compute systems, which are especially valuable for large-scale analytics, real-time ISR, and edge-based needs. The communication path on a single ecosystem will also be faster and more resilient than that of varied CPUs, GPUs, or APUs. Always, every time. What's more, the flexibility to scale the platform from data center to the tactical edge, from servers to laptops and embedded devices, means integrators and solution teams can deliver solutions with a common architecture across mission environments. This naturally improves sustainment, streamlines patching, and supports better cyber hygiene. From a U.S. federal perspective and a vendor business perspective, there are clear savings. Some report cutting hardware and integration costs by as much as $150,000 to $250,000 per deployment. Labor savings for the RMF package development and, don't forget, sustainment can range from 200 to 300 hours, and some teams are accelerating ATO timelines by 3 or 4 months. There's also a cybersecurity benefit. Fewer integration points means fewer vulnerabilities to manage. A unified platform helps enforce consistent configuration baselines, supports automated compliance checking, and simplifies continuous monitoring. That's critical when operating in a high assurance environment like the federal government, or aligning with initiatives like the, DOD, APL, Executive Order 14028, or M2209. All of these have cybersecurity benefits when we have an integrated platform. So the bottom line here on this slide, we have 3 other slides. The bottom line is moving towards a vertically integrated AI platform isn't just a performance decision. It's a strategic move that saves time, reduces risk, and supports mission execution. For integrators and solution teams working across the federal space, that kind of efficiency is a real force multiplier. And just before we go to the next slide, a security advantage. Remember, a streamlined stack helps enforce consistent patching, fewer update cycles, and reduces the attack surface, all critical during sustainment. Okay, point 2, open source software. Now, one of the most efficient ways to streamline AI deployments in the government or defense environments, or frankly any environment, is by adopting an open software ecosystem. When teams choose open source AI frameworks and tools, they gain visibility, flexibility, and control that proprietary platforms often don't offer, especially when navigating the ATO process. Open source is not an enemy to an ATO. In fact, in 2025, it can be a real game changer. Open GPU computing platforms, such as those built on open source standards, have matured significantly over the past several years. Earlier versions were not as, performance oriented, but these tools now offer serious throughput gains, especially in training and inference tasks. With better integration into mainstream frameworks like PyTorch or TensorFlow, developers can now deploy models using standard libraries without needing to customize or rebuild code for the platform that runs on the GPU. That kind of plug-and-play capability is a game changer for integrators and for solution teams under pressure to deliver quickly and securely. From a cybersecurity standpoint, the benefits are even more compelling. Open code bases allow for full auditability, making it easier to meet FISMA, STIG, and zero trust architecture requirements. Security teams can scan the stack, generate SBOMs, which remember is software bill of materials, which basically helps identify vulnerabilities quickly when new CVEs emerge, common vulnerabilities and exposures, and validate against compliance standards with no hidden code or vendor barriers. This reduces the need for manual waivers and accelerates steps like RMF Step 3, saving teams an estimated 100 hours or more per cycle. There's also significant cost efficiencies. By avoiding licensing fees tied to proprietary SDKs, remember that proprietary SDKs can increase risk through hidden code, delayed patches, vendor lock-in, and limited auditability. Organizations can realize savings of $500,000 or more annually. These savings aren't just in licensing. They also appear in reduced documentation time, fewer revalidation cycles, and simplified sustainment planning and execution. For teams building AI capabilities in sensitive environments, classified, compartmented, or otherwise highly governed, open ecosystems offer long-term sustainability. We're not tied to a single vendor's roadmap, and we gain the ability to modify, optimize, or extend the toolchain based on the mission need. This approach supports a more secure DevSecOps pipeline, enables crisis changes to the AI environment, enables faster patching, and improves reproducibility without compromising functionality. So what's the best practice takeaway here on this slide? If you're building an AI system for federal missions, consider open source software stacks not just for flexibility, but for faster ATO approval, lower lifecycle cost, and stronger cyber posture. It's a smart way to reduce friction and stay aligned in a mission-oriented, compliance-heavy environment like SIPR, NIPR, or JWICS. Remember, the security advantage here is visibility at the code level, supports SBOM generation, STIG alignment, and a more defensible cybersecurity posture. So let's flip over to the third point here. We got one more after this. There's only 4 points. I appreciate you staying on here. High throughput. Now we're moving kind of into, this is how it's done, right? And we're going to talk about throughput and memory. But here, when deploying AI and advanced analytics, the strategic use of platforms that combine robust multi-threading and high memory bandwidth will make a difference. This approach isn't just about raw speed. It's about sustained, predictable throughput under mission-critical workloads. And for those of you that are using AI systems and have to preload, for example, browser tabs just to get the data to flow properly, or tell everyone else on the network to stop working until you're done with this presentation, this is an answer to that problem. In AI and defense use cases such as ISR data pipelines, real-time cyber threat detection, and command and control systems, workloads are highly parallel and data intensive. A platform with high core counts and advanced multi-threading allows these tasks to execute concurrently, reducing bottlenecks during pre-processing, inference, or streaming analysis. Instead of queuing tasks across underpowered cores or distributed nodes, you're handling them head-on with compute density that scales. Equally important and high is high memory bandwidth. AI workloads, especially large language models or sensor fusion analytics, aren't just CPU/GPU intensive. They are memory bound. When the system can't feed data fast enough, even the best processors stall. That's why newer architecture are delivering memory bandwidth in the terabytes per second range, allowing massive data sets to move through the pipeline without delay or fragmentation. The real impact with a focus on throughput, fewer servers are needed. In many deployments, integrators are replacing 4 to 5 older servers with a single high-density platform. That's a power reduction of approximately 65%. It shrinks rack space, simplifies system management, reduces power and cooling, and cuts generally annual sustainment labor by 10 to 15%. It also reduces procurement complexity, as you need fewer boxes to hit mission performance goals. As we navigate the ATO process, this also streamlines compute environment, accelerates RMF step 4. With fewer nodes and simpler architectures, validation timelines shrink, and testing teams spend less time mapping performance edge cases or writing mitigation plans. There's a cybersecurity win here too. Fewer nodes mean fewer east to west connections, reducing lateral threat vectors. High throughput platforms are also more resilient under cyber stress, able to maintain availability even during surges, scans, or anomaly detection workloads. In short, if you're architecting AI for government use, especially in a DDIL/disconnected enclave or tactical environments, prioritizing high bandwidth can deliver performance, compliance, and security while lowering cost. So when building or modernizing infrastructure, consider it a best practice to prioritize multi-threaded compute and memory optimization designs. It's one of the smartest ways to align your AI stack with real-world mission demands. And here's the security advantage. Reducing horizontal sprawl also cuts down lateral movement risk and simplifies network segmentation strategies. And certainly, last but not least, large onboard memory simply simplifies deployment. So this, again, is a how it's done point. But in today's AI landscape, many teams are facing a common challenge: how to run large, complex models securely and efficiently, especially in environments where data movement is constrained, like classified enclaves or edge deployments. A best practice that's gaining traction involves leveraging AI-accelerated GPUs with extremely high onboarding memory, specifically those offering 192 gig or more of HBM3. Why does this matter? Because traditional GPU architectures often require models to be split across multiple cards, which increases infrastructure complexity, data movement, and the burden on security assessments like an ATO. But the ultra-high memory GPUs, large models such as LLMs or image classifiers, can be deployed entirely on a single GPU. This simplifies architecture and makes it much easier to meet compliance and security boundary requirements. In practice, really, this approach offers three major advantages. One is a simplified architecture and an easier ATO. Look, simply, with fewer GPUs and interconnects involved, the system boundary becomes smaller and easier to define during RMF documentation. This can save 30 to 50 hours in ATO preparation and reduce long-term sustainment costs by limiting the number of components required in patching or vulnerability scans. Number two, reduced cost and higher efficiency. By consolidating workloads into fewer cards, integrators avoid the need for expensive interconnect hardware and large-scale clustering. Reports show that potential savings of $400,000 to $600,000 per cluster, depending on the workload and, of course, deployment scale. This efficiency helps teams stay within budget without sacrificing performance. And number three, stronger cybersecurity posture. Look, fewer moving parts means less data in transit, which reduces the risk of interception and exfiltration. This is especially important in air-gapped or SIPR environments where data locality really does matter. These high memory cards also support compartmented model execution, aligning well with security expectations in classified or sensitive settings. What we're seeing is a shift towards platforms that are designed with mission security in mind, not just raw performance. The ability to host massive models on a single device aligns with evolving federal use cases, from disconnected edge AI to secure enclave-based analytics. As AI workloads grow, this best practice, choosing platforms with enough onboard memory to simplify security boundaries, will become even more critical for delivering scalable, compliant AI into the federal space. Just our last security plug here: minimizing data in motion lowers the risk of exfiltration and helps teams meet enclave-specific data handling requirements. Look, ultimately, building secure, scalable AI for federal isn't just about the compute power. It's about selecting a platform and ecosystem that aligns with cybersecurity expectations, ATO workloads, and operational realities. When those pieces of the puzzle are in place, teams gain speed, security, and confidence at a lower total cost.